Welcome. This is Data Hiding with Steganography. My name is Justin Clark. And this is my final presentation for Computer Forensics 1 at the University of Central Florida. Just what is steganography? Well, I'm glad you asked that, imaginary random person. Steganography is the practice of hiding information within other information, ranging from secret messages written in vanishing ink to illicit images embedded in innocuous photographs. Unlike cryptography, which obscures the content of a message, steganography obscures the presence of a message. Early steganographic techniques include the ancient Greek practice of carving a message on a wooden tablet, which was then covered in wax upon which a second fake message was carved. In fact, the word steganography originally referred to this very practice. Eventually, more sophisticated techniques appeared, such as writing text using vinegar or fruit juice for ink, such as lemon juice, which becomes transparent on evaporation but darkens when exposed to a flame. Another popular method in the Cold War was printing entire photographs or documents in microdots disguised as punctuation marks. Another time-honored technique is using specific letters of each word in a message to spell out a second message, such as in a newspaper crossword puzzle. This is known as a null cipher. It was used both in real life and in spy novels and mystery novels and movies. Our focus, however, is of course on digital steganography. Adding bits to a file is a common approach to embedding secret data. This is normally done in the file headers and after the ending of the file by concatenating additional data onto an existing file. Embedding information in audio formats such as MP3 or WAV can be done by adding echoes or other noise that sounds natural in the recording. Another method is hiding data in the least significant bits. Because not all bits are necessary for image files, or audio files for that matter, data can easily be hidden in the remaining unused bits. Closer look at the LSB technique. Data can be nearly imperceptibly hidden by modifying least significant bit of the RGB color channels in a BMP or even a PNG file. Here we have a BMP image with a 24-bit color channel, 8 bits given to each color. And by flipping the values of the lowest bit, we can change the colors in a way that the human eye does not detect, but which has some meaning. They may spell out a message or conform to an entirely separate image or even a document. From a discrete mathematical perspective, there are basically two steganographic functions illustrated here. The embed function requires as inputs the secret message in a set of all possible messages, a plausible cover in a set of all covers transmissible over a given channel, and a secret key from a known key space. The embed function outputs a stego object, which is indistinguishable from, but not perfectly 100% identical to the cover object. Once this Stego object is received, the recipient then simply reverses the process with an extract function, using the secret key to retrieve the original message. From a practical perspective, this key, mathematically defined, may not in fact be a key in the same sense of a cryptographic key. Starting, I believe, in the 2007 version, Microsoft Office has used an XML-based format for many of its popular applications, including docx for Word, .xlsx for Excel, and bbtx for PowerPoint. These files are essentially zip-compressed containers, or archives, containing raw XML and related configuration files. In much the same way that a web browser renders raw HTML into a web page, Word and other applications render the raw XML into a document or spreadsheet or presentation, according to the whatever application you're using. Because of this, we can use a very low-tech steganography technique, which I will demonstrate hereafter. So here I have a cover file in the form of a Microsoft Word docx, and I have an image that I want to embed. Now, because docx is basically a zip archive, we can open it in any zip utility. In my case, I'm using 7-zip. And to hide our image, all we have to do is drag and drop over here. Now, we could stop at this point, and I'll show you how that works. But as you see, when we try to open up the Word file, it's unreadable. Since our objective here is to hide data without drawing attention to itself, we have to consider this a failure. So to do this the right way, we need to make one additional change to the file. And that is right here, this XML file. We need to add one little line. Right here, which contains the path and the file name of the image that we simply embedded here. Now we modify the original archive. Now, when I attempt to open it up again in Word, we can see now that it is completely indistinguishable from the original cover file. In fact, none of the changes we made, other than time, will appear in the file properties. And we can see that the file is slightly larger. It was originally 176 kilobits. But if someone doesn't have access to the original, they won't be able to tell the difference. Now I'm going to demonstrate hiding data inside a bitmap image using the LSB technique mentioned previously. One could possibly do this manually with a hex editor, but I'm going to use an open source program called Hide in Picture. So let's begin. We've got our cover image of a Stegosaurus, which previously appeared in the presentation, and we have a secret message that we want to embed. So we've got to get the truth out as soon as we can, so let's open it up. So here's the unmodified cover image. We want to use the embed function here. Put in our secret message. Now, the password is entirely optional here. You can leave this blank if you want. But just for the sake of demonstration, I'm going to use a password. And the program automatically encrypts the secret message so that even if it is recovered, it can't be immediately read. And we have our choice of using either Blowfish or the Rheindahl, that is AES ciphers here. And I'm going to use Rheindahl. So here we go. Whoop, mistyped my password. Oh yes, before we, in order to complete this, we have to save the image. So now we have cover image, modified image, completely indistinguishable from one another. Same size, they look the same, maybe a slight difference, I can't see it. The properties, the only thing we can see different is the actual dates, time of when the file was modified. Same size, same color, bit depth, etc. Just the time of day when it was created and modified. However, if we do a command line comparison, we can see that we have changed specific bits, changing the least significant bit in each case, E to F, etc., C to a D, blah blah. And we can run the same program to recover the original secret. We just do the process in reverse, retrieve file from picture. We enter our password. And we tell it where we want to save our and voila, same message. For my final demonstration, we'll be taking a look at audio files. Here we've got our cover audio, which is just a simple wavetable of the level 1 theme from Altered Beast. And our secret message is the same as last time. And once again, I'll be doing this with a program, this time using Deep Sound, version 2.0. So let's take a look. Here's the interface. Our carrier file, we have to select a carrier, which is our WAV file. Then we add secret. And as with the previous demo, we can encrypt it with a password or not. In this case, I won't be using a password. And now we have two versions. Now I'll just change the name of this message file, get it out of the way. If we listen to the new modified audio, we can't tell any difference. Has the same length, same sound, at least to my ears. And barely even registers in fact, it doesn't register any change in size at all. Only the timestamps are altered. And using the same program, we can extract the original secret. This time we open up our modified file. Now we see that we have an embedded text. We can extract it. And here we have, once again, the recovered text, exactly as it originally appeared. Advantages and disadvantages of steganography. Steganography can be difficult to detect because it does not look like it is out of place compared to an encrypted message. That is, there's not a whole lot of jumbling going on. The medium of transmission, unfortunately, is potentially destructible without a chance of recovery. For example, in the case of the Word document we modified earlier, if someone found that Word document and was not able to read it due to the improper modification because we didn't edit the XML, they might delete it and then re-download the original unmodified docx. And the use of steganography alone is really a form of security by obscurity, which InfoSec professionals know is no security at all. And it's only secure if nobody is aware of it. To be truly secure, steganographic and cryptographic techniques must be used together. And as we saw with the previous programs, they do in fact use steganographic and cryptographic techniques simultaneously. And there are possible delays in transmission for non-digital techniques. For example, having to send something through the mail or get it printed up by a newspaper or having to go to a dead drop, etc. Lots and lots of delays. And it is also relatively easy through steganalysis to reveal if a file is hiding information by comparing the payload to a known clean original, or if the payload is relatively larger than it should be. Now, the examples I've used here did not change the size of the original file by a great deal, but it is possible to add many megabytes or gigabytes to a file. If the cover file is much larger than it really has any right to be, then that may be suspicious. Ultimately, the primary factor in determining the security of steganography is the ratio of inert data to hidden data. Patterns in the hidden data are also relevant, as these can provide clues to the original message. When there's more hidden data than inert data, it becomes more likely that the hidden data can be detected and thus recovered by someone who should not see it. Solanke and others in their paper cited later showed that steganography can be rendered more secure by matching the probability density functions of a composite signal and the original signal. If both signals are close to or have exactly the same PDF, then hidden data becomes nearly unnoticeable within the inert data. And the chart at left comes from page 127 of that paper, which appears in the bibliography. And there's the bibliography. That's about all I got, so thanks for watching.